Okay, so let's call this part 3 of this course on Introduction to Climate Science, Modern Climate Change and Climate Modeling. This is a book from Thomas Stoker. Tom Stoker was IPCC chair, I think, for the 2007 release, if I'm not mistaken. 2014 was Pachauri, I think. Either way, he had advocated that maybe IPCC needs to rethink how to do things, and I know him from my days at Columbia University, just as a personal note. I think you have some idea of what climate modeling means, or weather modeling, especially weather predictions. When we talk about the future, we are not throwing a dice to make forecasts, predictions. So obviously there is a representation of the weather which we run on a computer model, and then we integrate forward, let's say starting now, into few hours later, tomorrow, few days later, and so on. And for climate modeling, we do the same thing for a season later, multiple seasons later, and for climate projections, we do multiple decades into the future. There is a chopper going by which is far enough. So let's start with the first chapter, which is just an introduction to the basic concepts and a bit of a history of the key figures that played a role in the evolution of climate model. And 2020, as you know, was another banner year because climate scientists got a Nobel Prize in Physics, Suki Manabe and Klaus Hasselmann, who had done some fundamental work. So we'll mention Suki Manabe here. So what are the most important components and associated processes that we are trying to represent in a climate model? There are governing equations that we will see later on, which often cannot be solved analytically. So we need to discretize them and put them on a computer and then integrate them, which means the sphere has to be represented in what are called the grids that we will see, and so on. And each grid is going to represent climate, which includes all these processes which we looked under the climate system, for example. So there is energy coming in and there is energy going out, which is the main driver on top. And then you have within that, of course, the land surface, hydrosphere, which is the all the water. You have cryosphere, which is all the frozen water on land and sea ice and mountains, and so on. And you have the anthroposphere, which is now a critical part of the Earth system. So human activities are beginning to act as a forcing, which means they are beginning to change the balance at the top of the atmosphere. Typically, when we say forcing in a climate context, we mean anything that changes the balance of energy at the top, because that means it translates to warming and the cascading effects on winds, humidity, rain, sea level rise, glacier melt, and so on and so forth. And we have many details like albedo, the reflectivity. Ice and snow have high albedo, desert has a high albedo than forests, for example. Then we have all the chemistry of greenhouse gases, and we have exchange between the vegetation and the atmosphere, not only of chemicals like carbon dioxide, oxygen, methane, etc., but also water vapor. And we have aerosols from human activities like coal burning, land use change, deforestation, agriculture, and also from volcanoes, which are natural forcing, and so on. So climate models basically try to take all these processes, and they have obviously evolved from simplistic representation of these processes and have become become more and more sophisticated and complicated by now. They include many processes, and they don't get they're not just climate models anymore. They are in fact becoming Earth system models, though, so they are even beginning to represent the cryosphere, glaciers on land. Sea ice was easier to represent, glaciers are harder, and so on. And there are still many details that we will go through. What is remarkable is that models are not perfect. They are numerical representations, and often there are process understandings missing, like going from molecular scale interactions between water vapor and cloud condensation nuclei, forming clouds, convection and rainfall, and so on, and how aerosols affect the scattering of light or absorption of energy, and how they affect the cloud condensation nuclei, droplet sizes, cloud processes, and even other processes like cyclones, and so on, and how vegetation affects albedo, affects chemistry, affects energy balance, and how the ocean affects climate, and so on and so forth. What is remarkable is that given the energy at the top of the atmosphere, the climate models, which are representing the major spheres like land, hydrosphere, cryosphere, atmosphere, and so on, they are able to reproduce the large-scale circulations, monsoons, El Nino, and other kinds of modes of variability that we mentioned before. So even though they are not perfect, they are remarkably good. We will see how they are combined for making decisions at various timescales, at weather timescales, climate timescales, and for the future. So with that introduction, maybe I should stop here and come to the scales in the next podcast. We will see that even in the Earth system there are various levels of complexity. So there are what are called EMICS, or Earth system models of intermediate complexity. So we have introduced now jargon climate model, Earth system model. So usually when we transition from climate model to Earth system model, the most important thing that is added is the carbon cycle. And the carbon cycle can be done as just the chemistry or vegetation and chemistry, and the vegetation itself can be done as simple representation of vegetation types that are fixed in time, or you can have what is called dynamic vegetation, where vegetation is responding to climate variability and climate change, and change in its composition, for example, C3 plants, C4 plants, and so on. Again, if you don't know what that means, don't worry right now. It's just how many carbon atoms are involved in the photosynthetic pathway, and there is reasons why they evolved over time this way. It has to do with energy efficiency, temperatures, availability of CO2, and who can compete better when during high CO2 and low CO2 and so on, which of course has a great relevance for what we are doing now in terms of increasing CO2 and warming. And we have to understand how vegetation responds, especially crops, agriculture, food production is being seriously affected by climate change. So we have to worry about those sorts of things as well. So without getting too much further, let me stop here and then come back and go through the processes and look at the scales. As we know, we have to go from molecular scale to planetary scale, which is many orders of magnitude range, and it's argued that climate system or the Earth system has a larger range of scales than the entire universe. So that's what we're trying to represent. So we have to make some room for the fact that there are missing understanding of the processes, so we cannot properly model them, or often the model, the process is represented in a way that is not totally perfect, or because we are doing it numerically and representing Earth as a number of boxes, the number of boxes can be limited because the computations involved and the computing power needed to run a model with many boxes increases exponentially. So we optimize the number of boxes and the processes we want to capture. So what you want to do with the model, what processes are important for you, and whether you are trying to understand processes or actually predict weather and climate, it's all going to be involving different choices as well as different uncertainties, outcomes. Words like bias and uncertainty are used by modelers, but they can be misconstrued, especially by people who want to argue that climate change is not happening and models don't know what they're talking about, and so on. But remember that models reproduce everything about the climate, and even if they're not perfect, they are remarkably good at teaching us, helping us make decisions and project into the future. Okay.